Here, we want to talk about normal distribution curves. One of the most important distribution that we use in the statistical inference is the Gaussian or bell-shaped curve. And you can see here, we have these rule of thumbs, and it's like that the probability of the x minus mu. So when, it's like that the probability, if it's between x minus mu, if it's between the like 1 sigma, like positive sigma and negative sigma of like a standard deviation. So we should have like 68% of the data points in that range. So it's like this. When we look at here on this curve, you can see this mu, right? Mu plus sigma, mu minus sigma. It means that if we want to have the normal distribution curve, it means that here, all of these parts, like these two, the area under the curve, under these two sections, it should be 68% of the data. 68% of the data points, it should be under here. When we say probability of frequency, the meaning is that. Right? For example, look at here, and then we say x minus mu between like 2 sigma and minus 2 sigma. It means that, look at these 4 sections, like four bins that you see here, if we say, like, or 4 histogram, area under the curve, so 95% of the data points, it should be here. And then the next one is that, like, for the plus minus 3 sigma, 99% of the data points should be here, should be under the curve. If not, we can't say that is a normal distribution curve. We are dealing with a normal distribution curve. It's very important that we have our data points are normally distributed, because if not, we cannot rely on the regression model or mathematical model or forecasting model, prediction model that we make based on the data point. So all of these, like regression model, forecasting model, those ones, all of these are the similar names that we use. It's the same. I'm just trying to use all of them that you would recall, all of these things that you have learned before. So it's like that we should, like, for example, we should have 99% of the data points between minus 3 sigma and plus 3 sigma, like a standard deviation. If not, we cannot say that we have normal distributions. Our data are normally distributed. So it's like that. It should have a bell-shaped curve, as well as covering these like amount of the data points, like probabilities. So the normal distribution curve, if you want to write down because here we have the curve, right? So the equation of this curve is going to be equal to this. And for drawing, like, find out what's this curve, like the equation of it, it's going to be, we would need sigma and mu. And then the reason that the equation of this curve is important is that because when we want to find out the probability, we need to get the integral from it. However, when it's normally distributed, the good thing is that we can go and use z-table instead of getting this integral. But still, we need to find out sigma and mu for it. So that's the normal distribution. Like, for example, look at here. So with different mu and sigma, we are gonna, for example, we are gonna get different curves. For example, this one, as you see here, this one, the curve shows us that it has a larger mu comparing to this one. So it's like that if the mu of this one is like 5, if the mu of this one is 10 point something or close to 11. So that's one thing that we need to consider. Another thing is that how would we write this? For example, for this one, we would write down mu is equal to 5 and the variance is equal to 4. So the way that we would, you industrial cases, you will see the same thing as well. It's like that when they want to write down, we have a normal distribution curve. So they're going to write it like this. They would say that n, 5 and 4. It means that it's normally distributed. It's not semi-normal. It's normal distributed, and it's with the mean of 5 and variance of 4. So one mistake that I see students they do when I give them questions in their exam is that they consider this 4 as a standard deviation because it has a standard deviation has the same unit as mu. So they would do this mistake. Just be careful with this. The first one is mu and the second one is variance when we are looking at it. The next thing, For this one, you see that n is 10, for example, mu, so mu is more, but standard variance and standard deviation is less. So the variance here is 1, and because of that, the standard deviation is the square root of that is going to be 1 as well. But it's like that the deviation of the data from the center, it's less. So when you see a curve, like bell-shaped curve that is like this, so it's wider, it means that the variance is larger. If it's like this, it means that the variance is smaller. So that's the normal distribution. When we want to use tables, think about it. We have data points, we have a wide range of the data points. We can have the data points that they are like, for example, is 1 million. Like the value of the data point is 1 million, 2 million. Or we can work with the, like in some experiments that we are working with the like small numbers, maybe our data points are in like micro. So what we do is that we want to have one general table for them. Like for example, if we want to use Z table, what do we need like to do is that we need to first standardize our data points. Then we can go to the Z table or T table or Chi square table or F table or K table, all of these tables. We can go there and use them. So for standardizing these tables, each of these tables, they have their own groups. Z table, which is a basic table, we are going to use it whenever we are interested in mean, and it's case 1 or case 4, we use a Z table. We are interested to find out mean of the population, and we know the variance of the population. It rarely happens in reality, but it's the basic one that we need to learn before going to the T table. So Z table, as we had it in the second year, in our second year course, we would say for transferring X from real word, like real data points, to the Z word, we would say that we use this equation, Z is equal to X minus mu divided by sigma. The beauty of it is that Z, the minimum number for Z when you get gather your data points is going to be -5. The maximum is going to be +5. But do you remember that we said that when we are working with the normal distribution curves, we want 99% of the data be between like -3 sigma and +3 sigma. It means that 99% of the data points that we have, the Z value of them is going to be between -3 and +3. Because of that, or it's going to be very close to 0. So our Z table, if you have, when you are looking at the Z table, I already posted the Z table on Learn as well, but in this 220 notes, you can see that we have something, it's in the stats table, so you will see that. But when you're looking at the Z table, you would see that it's, for example, -4 to +4 maximum of it. So we put X here, X minus mu divided by sigma, and then we go to the Z table and find out the probability for it. So we need to standardize our data points first. And here is that expected value for Z is the mu at Z, and then which is 0, and V variance value for the Z is going to be sigma 2 at Z, which is equal to 1. So it's like that. Think about it. If instead of X, I would put mu, so expected value for expected value is the same as mean, right? So it means that if my X is mu, it's going to be mu minus mu divided by sigma, it's going to be equal to 0. So and if you put it in the variance equation, so the variance is going to be 1 as well. So Z is called the standard or unit. We always use it as standard for normal random variable or normal unit normal deviate. If X is normally distributed with the mu and sigma 2, then Z is normally distributed with the variance, with the mean of 0 and variance of 1. And to look up probability associated with any normal random variable X, first transform to Z, and then look up the probability in a table. Value of Z are tabulated. So with the value of Z, make sure that you're going to look at Z table that I posted on Learn. But it's like that. It's going to be something like this. And I'm going to go through that quickly. We just cover whatever we have on this page, because we have an example and that's a good one. So here the example is that we have, let's say X is normally distributed and then the mean is 8 and the variance is 4. So we are looking for the probability of x less than equal to 10. So what do we need to do is that first we need to find out the value, like transfer this z in 10. Consider that 10 is the like English language, like in English language, and you want to transfer it to French. It's like that. You want to see what's going to be its different language, like different way. It has different scales in it. So it's like that. You would say 10 minus 8 divided by 2 is going to z is going to be 1. And then from z table, we need to find out the probability of the z less than equal to 1. So what I'm going to do, I'm going to make this one bigger. So instead of the probability of the x less than equal to 10, we can find out the probability of the z less than 1, right? Because a standardized value for 10 for that specific example was 1, based on the mu and sigma that it had. So we are gonna go to the table, and then in this table we want to read that what's going to be the value for the z less than equal to 1, right? Okay. So for this one, when we are looking at this table, okay, so if you know, it's going to take like 1 minute or 2 minutes that I would explain it. If you already know how to read the z table, you can skip this part and go to the next one. But it's like that the first column, like whatever you see on the first column and first row, it's related to z. Whatever you see on z table is like this. Whatever you see here, this is the probability value or the integral under the curve. So what are we going to do? We are looking for the probability of and it's cumulative, like the value that you read is cumulative. For example, we are looking right now for the z less than equal to 1. What I need to do is that I need to find out the value of z for 1 and then read the probability. So I would go here, 1 is this, right? And when you want to be here, we found that z less than 1, right? We are looking for the z less than equal to 1. If it was z less than or equal to 1 point, for example, 2, what I would do is that when you look at here, you can see that this is 1, 0 point, this is 0 0.1, like 1, sorry. So this one 0.1. So 1, and then it's 2, 3, 4, something like that. But if I needed to find out 1.2, I would need to add whatever value that I have here to this. So 1.2, it would be, here would be for the, I see reverse from when I look at the camera, like what's inside the camera. So it's like 1, I would say 1.2. The first one is going to be the value for the probability of the z less than equal to 1. This is for the 1.1. You can see that we have 0.1 on top, so it's you would add them. And then the next one is going to be for the z less than equal to 1.2. So this is how we would add these two. So for this case, for this example, when we are looking for the z less than equal to 1, we are going to read it for the 1, and it's going to be the first one, 0.84, 134, something like that. So this is going to be the value that we are looking for. So from z table, we read the z value for the less than 1, and then we would say, okay, so this value is exactly the same as the value that we would have if we were looking for the probability of the x less than 10. So what's going to happen? Let me just bring up the correct, this one. Okay, so when we are looking at it, it's like that. From the table, because the probability of z less than equal to 1 is 0.8413, so probability of the x less than equal to 10 is 0.8413. You could go and write down the function, real function based on a mu and sigma, and then get the integral of it. But who would do that? It takes lots of time to get the integral of a large function. Because of that, these tables is going to help us a lot. So if it was like between two, like it was like, you can always interpolate as well if it was between two numbers in the z1, when we are working with the z value. So another thing that I want you to do by yourself is that and then ask me if you have questions. For example, try to find out the expected value for Z. You know that I already told you this is going to be, the value of it is going to be 0. Already, if you go back, you're going to see that I told you how we calculate this, x minus mu divided by sigma. So instead I see, I'm telling you that. Anyway, just work on it, please. How to find it? Just replace the value for it, and the variance for the Z. So you're looking just instead of Z, put x minus mu divided by the sigma. And then for the variance of Z, the final, you should find out 1 for it. The final answer should be 1. Try to work on it and then let me know if you had any question. It should be very simple to find. And refresh your memory on using Z table. It's very important. Okay, here are other examples. You have the answers as well in front of you. So it's just for the practice. So here it says that if x is n, 8, and 4, like the same, similar to the one that we had before. We are looking for the probability of we are looking for some x, that probability for that is going to be 0.75. So in this case, what should you do is that when you want to work with the Z table, you will need to look at these data points. These are probability when you are working with the Z table. Try to find out 0.75 and then find out the related Z value for it, read it. So here is that the probability of the Z value for it is going to be 0.6745, and then put it in the equation of the Z equal to x minus mu divided by sigma. So you have Z equal to 0.6745. You can find that x from that one, right? And you can see that here we found that the x is going to be 9.349. As I said, you have the solution in front of you here, but try to find out for yourself to make sure that you can read the reverse version from the Z as well. So these normal probability rules, we had it before, like we talked about that. So this is it says that 68% of the data should be between like minus sigma and plus sigma, 95% should be between minus 2 sigma. These are probability rules, right? And then minus 3 sigma and the 3 sigma, 99% of data should be there.